Hi guys, this video to take you through the code that I used to produce lecture 3. So if you haven't watched lecture 3 in my econometrics course, so you need to watch the lecture first before following this video. So in this video, I'll show you how to create the same tables, the same graphs, the same results that you can see in my lecture 3 slides. As usual, you first need to activate the libraries that you need to use in this code. So first, I will activate all these libraries together. So now the libraries are active. Then we covered in this lecture heteroscedasticity, autocorrelation, and model specification. So with heteroscedasticity, we used food data from this package, principle of econometrics data, textbook data, and this package called POE data. First, we need to load the data. So the first line of the code just loads my data. We just use food data set, and I estimated the first model where it's a linear model where using all this, food expenditure is the dependent variable, income is the independent variable, and the data from food, and that's something we explained before, so we know how to do regression using R. We plot the two variables together, and we include the regression line, and this is something we covered in the previous video. So if you don't know what that means, just go back to the previous video. In this line here, I'm just calling the residuals from model 1, which the first regression I ran here. As you can see here, before I move to that, this is the scatter plot with the regression line. Now we just create a new object based on the residuals from the first model we estimated, and here we have the residual. At the same time, we could also create another object for the fitted values, which I called here y hat, and the way the function used to call it is fitted, and then between brackets I add the LM object, or the linear model object, which is mod1. And now I stored now these two values, the residuals and y hat, or the fitted values, in two different objects. Now I can plot these. First, the residuals against income, my independent variable, and this is how it looked in my slides. And here I'm using the function plot to plot the residuals against y hat, or the fitted values from that model. And this is the graph. So what we show here, okay, we say we have cross-section data, so we expect heterogeneity or heteroscedastic error term, or error term that doesn't have a constant variance. So we cover two tests: how to formally test for heteroscedasticity. So the first one is Bruch-Begin test, and in this line I'm just specifying the significance level alpha 5%, and here I'm just running the model again. I mean, you obviously don't do that. You don't need to do that. I'm just doing that because I was using this in different slides. So so you actually don't need that because you already have mod1 saved. So all what we have here, we call the residual squares, and again you use function resid and the name of the object, and then the square. So this is raised to the second power, and then here the test equation. So we run the residual square on income. So remember, we created the residual square here, and thus here are the number of observations based on that model. So number of observation here is in OBS, that's number of observation, that's a function that can call the number of observations. And here we just tidy up a bit this regression, And now this is the number of betas, k or s, the number of betas, how many betas you estimated in this line. And then this is the chi-square. So that again used function q c chi-square for 1 minus alpha, which alpha we define at 5%, and s minus 1. This is the number of parameters, number of betas minus 1, and here these are the residual square from this, and this is how you calculate the test statistic. So it is n times r squared from this regression, and here is the function BP test, and then we put between bracket the object, and in that case this is exactly the same table you see in my slide. So it's very straightforward. So the decision, so you get the test statistic, and you got the p-value, and as we said in the lecture, you could just use the p-value to make a decision. So the null hypothesis is homoscedastic error term. So if you have a small p-value, as the case we have now, it's less than 5% and definitely less than it's even less than 1%. So that means we reject the null hypothesis in this case, which means the errors are not homoscedastic, they are heteroscedastic. So we have heteroscedasticity here. So we did the same using white tests. So we just repeated the same procedure. This is all to same for the same reason. And then in this case, you just, these are the number of parameters, k equals 3, and the method, and then you just create the second table for white test. So in this case, you can see the p-value is small as well. Again, so you reject the null hypothesis, the same homoscedastic error term, and you reject that using white test, and that confirms what we found using the Push-Pull-Again test. So both tests give the same conclusion. And then we discuss how to correct for that by applying the heteroscedasticity consistent standard errors, and we explain that the main issue here is that the standard errors are not reliable in the presence of heteroscedasticity. And what we could do here is we could use the HCCM. Again, this is heteroscedasticity consistent errors, and we could actually produce the same regression exactly as the one we had before, but this time we we use the heteroscedasticity consistent standard errors. So if you compare this one here, you'll see with the previous one, you see we've got the same coefficients. So this is the first one here, and this is the second one. So you see the first one has the same coefficients, the same estimated coefficient, but the only difference is the standard errors. So you see these standard errors here are different from this one. These are the corrected ones for heteroscedasticity. And that was the first point we covered in the lecture. So the second point we covered in this lecture was autocorrelation, and as you can see, these are the slides. And the first thing we did here is to call the data. We used Ocan data from the same package, and here I plot both the two variables, growth and unemployment rate. So let's see how we do this using the R code. So here from this, okay, so we first call the data, and then in this line here, using the data, I'm using the same data, I'm converting it to a time series object. So it is the Ocan, the same I'm using for start date from 1985 quarter 2 to 2009 quarter 3, and this obviously is quarterly data. And in this line here, I'm just plotting so you see here we've got this object here, which has two series here, the growth rate and unemployment rate. And all what we need to do here is just to plot the first series, the growth rate, and that's what you saw in the lecture. And here how you plot, use the function plot to plot the, so obviously we learned this before. If you want to call an object or a variable or a column or inside an object like what we have here, OpenTS, all what you need to do is just to, okay, so this here, the first, it's the number of rows and number of columns. So in that case, we call all the number of rows, so all observations, and here this text say, okay, go and find that column that's called U, and that's what you want you to plot. So that's exactly what we see in this line. Just I'm repeating this again in case of if you forgot or if you haven't, if you didn't follow my previous videos. So that was the first part. So that was the first graph, and then we basically just plotting a scatter plot of G and its lags. So I'm creating the first lag and the second lag. So this one is G, so the growth rate with the first lag on the vertical axis. Here is the second lag again with G. So let's see how we do that. So first we need to create this first lag and second lag. So this, obviously I'm creating a new data frame that's called GGL1, and in this data frame I'm combining these two variables, G, which is from the OpenTS object, and then I'm actually adding also the lag of the same variable. And so this is the first lag here, -1, and then in that case I created a new data frame that called GGL1, as you can see here, has these two columns. So you can just here, I'm just changing the names. So the names for GL1, I'm gonna call it, you can see here, is not really, doesn't look nice, the name of the variable. So all what you need to do is just to name them, and here we go. So one is G and the other one is GL, or the lag, and obviously the first observation is missing because this is the lag. So this is G in time T, and this is T this is G in time T -1. That means this is the lag from this one. So if you plot GGL1, that's what we got. So again, so it plots G against GL1, and we're just adding these lines here from the slides, if you can see. So this is actually easy to do in R. So that is the mean, and then I'm just adding the line, and as you can see, this is the first line and the second line, as you see. So that was just replicating or reproducing the same graph that you've seen in my slide, and this will produce the other graph. So it's exactly the same. All what I did here, rather than using only one lag, I use actually two lags. So in this case, and again, you rename the columns, and then you plot the graph, and then you use these lines to add these lines here. Okay, so that's great. So this is the first one of these slides here where you can see the scatter plots between G and its lags. Then we explained what happened when you when you apply all these estimators, estimation if you have serial correlation or autocorrelation. And here we use the correlogram to detect for autocorrelation. So how to produce that? So let's see how to produce this. So this is the growth rate. Again, I'm just taking the one variable, and then I'm just showing the autocorrelation function, and that's what you see in my slide here. So this is the graph here. So then we talked about Durbin Watson, and then we moved to another example using Phillips data, and which is quartile data from 1987 quarter 1 to 2009 quarter 3, and I plot the data first. So this is inflation, and this is the change in unemployment rate. So what I'm going to do now is to call the data. You now know this step now, so we call the data first. Oops. Okay, and then after that you can convert this to a TS object, start date and end date, and the frequency is quarterly data. And then I'm calling it, I'm just creating a new object called inflation that will actually pull this variable from my data set. So now we have inflation and the change in the unemployment rate, and then you plot inflation, use the function plot to plot inflation. This is exactly the same figure, the same graph you see, and also you can plot the unemployment rate that way. So exactly this is what we've seen in this slide. So here this is just a summary of the model, giving the I estimated this model here. So inflation regressed on the change in employment rate, and this is just a table to report the results. These are the estimated coefficients, the standard errors, statistics, and t-statistic, and the p-value. So let's produce this again. So you just load the library we need for this, for the dynamic LM, and then I just called create a new object called fill.dynam. So you can actually call it whatever you want, and I'm using the function dynlm, and then you can see here inflation is my dependent variable. The difference of u is the so there's a change in u is the, or the employment rate is the independent variable. And once I do that, I could actually create the table using the cable function here, tidy from the same object, and then I give it a caption, and that's exactly what you've seen here in the slide. So let's move to the next slide and see what we have here. So what we have here, we have the E hat, so the residuals against time, and we have here the program again for the residuals. So let's see the part of the code that can do that. So plot E hat. Obviously, I created E hat, which is the residual. Use the function resid from this object, the regression object, and then that will plot our graph, and then we just add the horizontal line at 0, as you can see here. So we could do the same, using the same object E hat to plot the program. So here I'm actually saving it in an object called that, and then I'm using this to plot. It's actually plotting here anyway. So it plot this is the second this is the correlation here for the residuals. Okay. So now the Durbin-Watson test, how to do the test. So it's very easy. You can use this dw test function, and here you don't need actually to do this step again because we already have this. So again, I explained that before. Sometimes I have to do it because I'm creating a new slide, so I'm reporting the results in a new slide. So I'm just worried that I might have duplicated names, and that would replace the old one, and then probably I'll get weird results I don't expect. So anyway, so what we did here is the Durbin-Watson test for this object, and which is my model here. This one, if you remember, we regressed the inflation on the change or on a change in unemployment rate, and that will tell us so the null hypothesis, we have a very small p-value, so you reject the null hypothesis of no autocorrelation, so that means we have autocorrelation. So that was the first test, the autocorrelation, the Durbin-Watson for autocorrelation, and then we move to discuss the Bush-Godfrey LM test for auto correlation, and we produce this table. So let me see if I can produce the same table again. So basically what we're doing here, just we're calling these from different types of the test as we explained. So these are just different ways of applying the same test, and when you do that we could, so we created these objects to pick up these test statistics, and here we just grouping them in one table, and yeah, I think this is just now putting them all together in one object, and these I'm renaming the columns, so method, statistic, parameter, and then the p-value, and then I'm just creating the table that you've seen in my lecture. So let's see what else we did in the lecture. Yeah, and then we corrected for serial correlation following HAG, heteroscedasticity, and autocorrelation, consistent standard errors, and we compare between the results. So, and this is how we do it. Just don't forget to load the library we need for this. And this one, okay, that one create the or generate these HAG estimations, which again stands for, remember, heteroscedasticity, autocorrelation, consistent standard errors. So, and that's what we this is exactly the same table we produced. Okay, so so that compare between different methods, and these are the incorrect ones, and this is exactly the table that we've seen here in this slide. Okay, and then we moved to the model specification. So the first issue we dealt with was the omitted variable bias, as you can see here, and that was the first table we produced. Again, so this was the correct model, where we considered this data about education income. I think it was about, yeah, so running the household, we run a regression of household income on husband education and wife education. So in this case, and the number of kids that less than 6, so these we assume that this is the true or the correct model, while for some reason we omitted other variables and we considered only one variable here, and then we see we show the omitted variable bias. We explain that how that affect the estimated coefficient. But now in this video, let's see how to reproduce this. So again, the first thing, we import the data, and the data here is edu income or education income, and we fed the first model. You remember the first model here has all the variables we think are important, or these are the correct model specification. So we assume model 1 now is the correct one, and then we estimated model 2 using only, and we omitted the other variables, and now we just produce the first table here, so that would give us the first table and with the correct model, and this one is the one that we omitted the important variables, and we should explain that in the lecture. So if you don't know what I'm talking about, so please go back to the lecture and understand first the omitted variable bias, and then come and see how to produce these tables in R. Then we move to talk about overfitted models, where you include irrelevant variables. And in this model, we try to generate, so this is the correct model, so this is exactly the same model we estimated before, but then we generated a few variables, 2 variables that are not relevant, so they are made up, so some random variables that they shouldn't affect family income. So let me show you how to produce the tables in this slides. And yeah, so model 3 here, this is the correct model, so exactly the same model we estimated before. And then this variable here, or this regression here, include two variables that are just, so they're not related at all to family income. And in this case, we just run the regression, and I already run the regression, and then I'm just going to report the first table. So this is the kind of the correct model, and this one is, you can see here, so this is exactly the model we've seen in my slides, and this one is the incorrect or irrelevant variables, as you can see. So we explained the consequences of this, and then we moved in the lecture to talk about how to test for this, and we can use the reset test. And here, if you don't know what that means, again, go back to the lecture, so to understand what the test does. But here I'm just trying to show you how to reproduce the same results. So I'm running the model here, so the model that we think is the correct model, and then we explain that would be the restricted model, and then we do the test, reset test, using the function reset test, and then we add only power equal 2, and that again you go to the look at the p-value, and because this is a small p-value, so you reject the null hypothesis. That means our model is not correctly specified. And again, so similarly, when we change the power terms, we add, again, it's still not, we reject the null hypothesis. And that was everything we covered in week 3, in lecture 3. So as I said, to be able to follow this this video, you need really to go back and watch the video, the lecture first, and the link for the lecture will be under this video. So please watch the lecture first, and then come and see how to create the same tables, the same results, the same graphs using R. Thank you so much, and I'll see you next week.